Deviation of actual cycles. From ideal cycles. Before we leave the matter of vapor power cycle, a few comments are in order regarding the ways in which an actual cycle deviates from an ideal cycle. The most important of these losses due to turbine, pumps, pipes, and condenser. These losses are discussed next. The first one, turbine losses. Turbine losses as described before represented by far the largest discrepancy between the performance of the real cycle and corresponding ideal Rankine cycle power plant. The large positive turbine work is the principal number in the numerator of cycle thermal efficiency and is directly reduced by the factor of isentropic turbine efficiency. The turbine work, W turbine, decreases with eta thermal second law or isentropic. Turbine losses are primarily those associated with the flow on the working fluid, through the turbine blade, and passage with heat transfer to the surrounding and also being a loss but of secondary importance. With heat transfer to the surrounding. The turbine process may be represented as this picture, where state 4 is the state after the ideal isentropic turbine expansion. Ideal isentropic table 4.4s. Isentropic is constant. Ideal isentropic turbine expansion. And state 4 is the actual state 4s and 4 actual state leaving the turbine flowing an irreversible process. The turbine governing procedure may also cause a loss in the turbine. Governing procedure. Particularly if a throttling process is used to govern the turbine operation. Throttling is used. Pump losses in the next section. The losses in the pump are similar to those in the turbine. And are due primarily to the irreversibility with the fluid flow. Pump efficiency was discussed before, and the ideal exists shown also in this picture for the pump. The ideal exit of the pump exit 2s and 2 is the real exit. Pump losses are much smaller than those of the turbine, since the associated work is far smaller. Piping losses. Pressure drops caused by frictional effect. And heat transfer to the surrounding. Are the most important piping losses. Consider, for example, the piping connecting the turbine to the boiler. If only frictional effect occurs, state A and B prime as this picture. The state A and B would represent the state of the steam leaving the boiler and entering the turbine. For example, we have leaving boiler, entering turbine, and temperature decrease cause to lose some work and heat. Note that the frictional effects cause an increase in entropy. Heat transfer to the surrounding at a constant pressure can be represented by the process BC. This effect decreases entropy. Both the pressure drop and heat transfer decrease the availability of the steam between the turbine. The irreversibility of this process can be calculated by the method in Chapter 10. A similar losses is the pressure drop in the boiler. Also, we have pressure drops in the boiler. Because of this pressure drop, the water entering the boiler must be pumped to a higher pressure than the desired steam pressure leaving the boiler, which requires additional pump work. Condenser losses. The losses in the condenser are relatively small. One of these minor losses is the cooling below the saturation temperature. Below the saturation temperature. Of liquid leaving the condenser. This represented a loss because additional heat transfer is necessary to bring the water to its saturated temperature. This represents a loss because additional heat transfer is necessary. To bring the water to its saturation to its saturation temperature. The influence of these losses on the cycle is illustrated in the following example solution parts. Cogeneration is the next section.